Okay, so now that we have methods for doing lots and lots and lots of derivatives, let's apply them. We did some applications already. We had our related rates ideas. We have our approximations. Let's go back and see if we can do some other kinds of derivative work. Talk about extreme values. If I graph an arbitrary function, I can ask, is there a highest point on the graph of this function? That's a legitimate question. Is there a highest point on this graph? Sure looks like it. Is there a lowest point on this graph? Maybe. If I assume this is the whole graph, it ends here and here, then yes, there's a lowest point. But if, as we see with most of our pictures, it continues downward, then maybe there isn't a lowest point. F of x has an absolute maximum value f of c. Boy, did I screw up and connect that c to the top of the parentheses. I apologize. If f of c is bigger than or equal to f of x for all x. I hope it is not beyond the realm of, well, clearly, what happens if I change this word from maximum to minimum? That's the only difference. Now notice that's not an x value. That's a y value. F of c. And these are extreme values, the overall highest, the overall lowest on the entire graph. But I've labeled, well, I've drawn 5 dots on this picture. My absolute maximum, C, is at this x value with whatever that y value is, right? I think this one is lower. So I would say that my maximum value is f of d. Sorry, my minimum value is f of d at x equals d. What are the other 3 dots? What does that mean?
It's that they're pointing tangent line to 0, but it's not.
I beg your pardon? I don't know squat about tangent lines at this point. I have no idea about tangent lines. You said the word relative. A relative maximum.
They're like highs and lows, but not highs.
Imagine, if you will, cutting the picture off. Now I can ask, is there an absolute maximum in here, in a neighborhood, in a local area, relative to the interval I've chosen? a local or relative maximum is chosen in some given interval. So it's local to the neighborhood we've chosen, relative to that interval. And if I change the interval, I can change the answer. If I asked in our picture for the local minimum in this pictured interval, we'd say the right edge, wouldn't we? Now what? Well, now it's the left edge, isn't it? Change the interval, you can change the answer. Finding them. I haven't done any calculus yet. I've just defined our terms. The graph, f of x equals x squared. It's parabola, right? There we go. Parabola opens upward, it's got a lowest spot. What's the name of the lowest spot on a parabola? The vertex. So the absolute minimum value is 0, and it occurs at the x value, 0. Using this same algebraic idea, this is another parabola. If I set that equal to 0, I find out where it crosses the x-axis. Algebraically, how do I find the vertex? I'm not doing derivatives. I said algebraically. No calculus required at this point. It's a parabola. Where is its vertex? I can look at the shifts, right? Parabola moves over, up, gets rearranged, gets stretched, distorted. I did this. Conic sections is chapter 11 of the trig book that we use here. Anybody remember how to do this? I know there's a formula. Aha, hiding in my quadratic formula, right? X is equal to negative b plus or minus a bunch of junk over 2a. Negative b over 2a, that's my vertex. Well, in this case, negative 8 over 2 times the coefficient in front of the x squared is a 1. That's negative 4. Take that, plug it back in. Oh, I'm not using f for this problem. I'm using g. G of x. So I plug in g of negative 4 and I get
Why is H equal to option?
The coordinates of the vertex are H and K, where H is the X coordinate, Y is the, K is the Y coordinate.
But say
Oh,
G of.
no, that should be a K. Thank you. That should definitely be a K. Typo, -1. Is this a minimum value or a maximum value? Why? It's quadratic. Parabola opens upward when the A is positive, downward when the, okay. I haven't needed calculus yet. If I'm giving an interval, then I'm restricting our picture. Draw the picture. I only care about what's happening between X equals -2 and X equals 4. So I'm going to rearrange the window here. Go from -2 to 4. I noticed down here in the bottom left that my graph is going off the bottom of the screen before it reaches the edge. And I noticed in the upper right, same thing, we're going off the top of the screen before we reach the edge. Means I probably don't have the right range of Y's to see everything here. But where's the absolute maximum on this interval? That is absolutely not the absolute highest point on this interval. At 0, 0, I have places over here that are higher than 0, aren't they? As a matter of fact, I can keep going. As far as I go to the right, I keep going up. I'm only allowed to go to 4. And if I hit trace and put in 4, I get 16. That's my absolute maximum. Similarly, I have an absolute minimum way over here. As we go down to the left, I have an absolute minimum. So let me rearrange the window to go from -20 to 16 in the Y's. And you'll notice that we go out each corner exactly. I hit the upper right corner. I hit the bottom left corner. I'm going out exactly at the corners. Those are my absolute maximums and minimums. But it does certainly look like 0, 0 is what kind of point? A local or a relative maximum. Yeah, that looks like it should be the two. And then it looks like we've got another local minimum floating around here too, right? Here. Looks like it's around 2. If I change the interval, I change the answer. If I change that, Instead of going from -2 to 4, to go from -2 to 2, then 0, 0 is my absolute maximum. Because that's the only highest point on the graph. Everything else is below it in this interval.
It would be you.
That's a really good question. But this theorem says if I have a continuous function, then it must have a minimum value and a maximum value somewhere in that interval. There'll be a highest and lowest point. I don't know what they are yet, but what this means is there's some point C, some point D, some X values that I will be able to find somehow where we have a highest and a lowest point. Why continuity? Okay, wait a minute. What makes a function not continuous?
If there's a break in the pencil, or if there's a value like a hole in it.
A break, a hole, a gap, or somewhere I got to pick up my pencil, right? A hole. Let's work with a hole. Here's a graph. We're only going to go from 0 to 1. I know. Here's a callback. At x equals a quarter, sound familiar? I'm going to put a hole. What is the maximum value of this function on the interval from 0 to 1? As I go from the left towards 1/4, I keep getting bigger and bigger and bigger and bigger and bigger and bigger. Do I ever hit that number? So how close do I get? As close as you bloody well want, right? There's a limit, but there's no actual value up there. I didn't put a y value up there, right? So, I mean, we could say maybe this y value is 1, but we never actually hit 1. Do we have a maximum? No. I do have a minimum, though, right? I have a minimum at 0, but I don't have a maximum. Are you ready for me to make it worse? Here's the graph of y equals 1 over x. But there's an asymptote there. And that means that as you get closer and closer to 0 from the left, you go down forever. And as you get closer and closer to 0 from the right, you go up forever. Does this function have a maximum or a minimum value between -1 and 1? It's got neither. That's why I need continuity. If I break the function anywhere, then I no longer can guarantee that I will actually hit the points I need. Only when my function is continuous am I guaranteed to get an actual maximum and an actual minimum. Page 282, figures 6 and 7. Good, look, there's a familiar looking picture. There's a hole, there's an asymptote. As soon as I run into these problems, but continuity fixes that. The way my instructor taught this to me is he said the continuous image of an interval. You think of an interval going from point A to point B, right? A continuous function takes that piece of the x-axis and distorts it and stretches it and twists it. That's what the graph is. It's a stretched, twisted piece of string. If it's continuous, it never breaks. And so it's still a solid piece of string. And therefore, it's got to have a highest spot and a lowest spot. Because you didn't break it. So, let me go back to that first picture. Emily, you said tangent lines.
Slope at any maximum minimum point has a horizontal line as the tangent line.
You've walked around the correct sentence twice. Really close. Wait a minute. At C, at x equals C, as I come in from the left, I get closer and closer to that point F of C. My tangent line, I'm going up. My tangent line has a slope that's positive. I'm off to this side. My tangent line has a slope that's negative. It should be horizontal to go from positive to negative. The intermediate value theorem says I got to go through 0 because it's continuous. Knew I needed continuity again. Same thing at D. To go from having a negative slope to having a positive slope, I should go through 0 when I'm continuous. A local extrema. Technically, the plural of the word extreme is not extremes. I don't care whether it's a maximum or a minimum. If you've got a local extreme at this point and you have a derivative there, then that derivative is 0. You said the tangent line is 0. not the slope of the tangent line is 0. And then you said has a slope that is horizontal. It's a horizontal line. You're real close on both of them. You meant the right thing. You just didn't say the right thing. And this is me being a pain in the ass.
Yeah.
Okay. We already know what the vertex of this particular value is. We know it's a local minimum for this function. Let's check, see if Fermat was right. What's the derivative of x squared? And we said it was at 0. Lo and behold. From our picture of the cubic equation, we thought we had a local extreme at 0 and another local extreme at 2. Take the derivative. And lo and behold, f prime of 0, 3 times 0 minus 6 times 0 is 0. And f prime of 2, 3 times 2 squared minus 6 times 2 is 12 minus 12, which is also 0. What's the derivative of x cubed? Say again. 3x squared. If I put in 0, I get 0. Graph this. Graph of the function itself. Houston, we have a problem. What kind of extreme is going on at 0? I don't know what the hell you're talking about. There is no extreme at 0. The graph keeps going up. It's not a minimum. It's not a maximum. 0, 0 is just another spot on the graph. It happens to be a place where we have a horizontal tangent line, but it's not an extreme. Is Fermat wrong? Why not, Jordan? Let's go back and read what Fermat says. If we have an extreme and the derivative exists there, then the derivative is 0. I've mixed up my conclusion with my hypothesis. My conclusion is that the derivative will be 0 when I have an extreme. We went the wrong way. I didn't know that I had an extreme in the first place. I just hoped I did. I don't for this function. So this is a problem. I need to take a little more care. In the same vein, graph the absolute value of x. What's this graph look like? It's not a straight line. Only part of it is a straight line. It's a V. It's two straight lines, not one. It's not like
Oh, it's the absolute.
as I said, absolute value. I did say that. Oh, no.
Thank you.
I have an extreme, don't I? I have an absolute minimum on this graph. But there's no horizontal tangent line. And sharp points are where my derivative doesn't exist. Again, Fermat isn't wrong. Fermat explicitly said, if I have an extreme and if f prime exists there. F prime doesn't exist at 0. It has an extreme at 0, 0. But there's no derivative there. There's no slope of a tangent line. Because if we do the derivative using the definition, we get a limit of 1 from the right and a limit of -1 from the left. The limit doesn't exist. Oh, crap. So unfortunately, it isn't enough to just look for places where my derivative is 0. I also have to think about, where's my derivative going to fail to exist? What's the behavior of the function around the points where my derivative is 0 or fails to exist? But I still want to count this somehow. I'm going to call these critical numbers. A number is a critical number or a critical value for a function if it's in the domain of the function and either the derivative at that point is 0 or the derivative fails to exist. So in our graph of the absolute value, x equals 0 is a critical value because the derivative doesn't exist there. In our parabola, x squared, x equals 0 is a critical value because the derivative does exist and is equal to 0 there. If I think of the point on the graph, c comma f of c, that is a critical point for f of x. Oh, that's an element symbol. A value X, it should be equals C. Boy, was I being sloppy. X equals C. Yeah, it was a bad symbol. I drew the wrong thing. C comma f of C is a critical point for f of x when x equals C is a critical number. So we talk about critical points on the graph of a function and critical numbers or critical values in the domain. With our cubic equation, that function is continuous everywhere. It's a polynomial. It's differentiable everywhere. That means there are no places where I have to worry about this spot. It's differentiable everywhere. The derivative is going to exist everywhere. I can find all the critical numbers by taking the derivative and setting it equal to 0. I only have to worry about solving f prime of x equals 0 to find the critical points. Because I can factor 3x out of this. Either x is equal to 0 or x minus 2 is equal to 0. So x is equal to 2, which means the previous version that I did where I looked at the graph and said, oh, I think those are the maximum and minimum, and those are my critical numbers, is exactly every possible critical number. Everything that happened outside that picture was going in the same direction. There were no other places where I had a horizontal tangent line, no matter how far to the right I went, no matter how far to the left I went. What was outside the little picture I was looking at, the little picture was all the interesting stuff. Everything outside of that was just questions. Here is where it is beneficial to me to simplify my derivative. I would like to find the critical values for this function. Advantage. X to the 3/5, a fifth root of x cubed, right? That's defined everywhere. It's not like a square root where I have to worry about things being positive versus negative. This is defined everywhere. If I want critical values, I need a derivative. And I need to look at where that derivative is either 0 or undefined. That's how I find critical numbers. So take a derivative for me. There are at least two different ways to do this derivative. Who's got a derivative for me? What'd you do, Nicolina?
3 fifths x or negative 2 fifths times -1.
Uh-oh. These are multiplied together. If I take the derivative of this, that's a product rule. Ike, what did you do? Go ahead, ask a question then. The only dumb question is, do I need to keep breathing? Ask. I could use the chain rule if there was a power on the outside of the parentheses. But since the outside of the parentheses is just a 1, I don't actually need the chain rule. Just product rule at this point. I certainly can do it by the product rule. There are other ways, regardless of which way you choose to do it. We'll do it another way as well. If I do the product rule, we'll come back. 3 fifths x to the, I got to subtract 1. Leave the 4 minus x alone, then leave the x to the 3 fifths alone. Take the derivative of this, 0 minus 1. Ew. But I'm going to do something with it. I'm either going to try and figure out where this is equal to 0 or where this is undefined, which means leaving it like this sucks. So I'm going to put the negative power in the bottom. Yes? And a -1 with a plus sign makes it a minus sign. The 3 stays on the top. I need the 5 on the bottom. Doesn't help if I don't have the 5. Copy error, important. I'm subtracting. I need a common denominator. What do I do to this to make it a common denominator? And the 1 I'm going to multiply by is 5x to the 2 fifths over 5x to the 2 fifths. That way the denominator will be the same. This will be stuff over 5x to the 2 fifths. Three fifths, 2 fifths, multiply with the same base, you add the powers. That's x to the 1. Which makes this numerator, oh, nope, that's x to the 1. Don't forget the 5. That's twice now, Avery. I've forgotten the 5. Gotta keep this 5 around. X to the 3 fifths times x to the 2 fifths is x to the 1. Hey, wait a minute. That makes this 12 minus 3x minus 5x is minus 8x. 5x to the 2/5. Yes, Nicole. Because that fraction up there at the front of this line says 3/5. That means the 5 stays on the bottom, doesn't it? 3/5. Yeah, that 5 there becomes this 5 here, this 5 here, and this 5 here. Yes, sir. Until. You're here.
Look outside that X to 3 skid, and I feel 5x over 2. Now here's my thinking. Multiply left side, right side, cancel out.
I didn't cancel it out. That's why it's on the top and the bottom. I put it here as a 1. Remember, if I multiply by 1, I don't change things.
Yeah.
So rather than just try and cancel, I said I want the bottoms to be the same. If I'm going to multiply on the bottom by that thing, I need to multiply on the top by it as well. Okay. Whew. Now, this is not the only way to do this problem, because I took the derivative in my notes a different way. If I go back up here to f of x, I can multiply this out. And I can write 4x to the 3/5 minus x to the 8/5. Multiply those together and you get? When I multiply together, I add the powers. 3/5 and 2/5 is 5x to the first. If I do this first, I don't need the product rule. I don't need the product rule if I do this first, because here, what's f prime? It's multiply 4 times 3/5 x to the minus 2/5, and then 8/5 x to the 3/5. Right? So this is 12/5 x to the minus 2/5 minus 8x to the 3/5. Negative powers go in the bottom. I'm going to end up exactly the same place. It's just the algebra that's different. I need a common denominator again. Oh, it's my 3rd time forgetting the 5. This 5 is going to be the death of me. What should I do here?
We've got to multiply 5x over 2/5 times, so 5x 2/5 over 5x over 2/5 to the right side. You got to multiply to the right side. Yeah, that side right there.
Except I already have the 5. Give the man a cigar. And what happens when you multiply these two x pieces together right here? And I get right back here. Remember, I want to find the derivative to do what with it? I already did my derivative. I don't need a power rule again. I already did the derivative. I need to know where this is 0 or where this doesn't exist. This is a fraction. Where does a fraction not exist? The bottom is 0. F prime of x does not exist when the bottom is 0. Divide by 5. X to the 2/5 equals 0. But the only way x to a power is 0 is when x is 0. That's critical value number 1. But wait, there's more. A fraction is 0 if the top is 0. If these are my critical values, my graph should reflect two different behaviors. I have a place where my derivative doesn't exist. Either I'm going to get a vertical tangent line, a corner, or a jump. Wait a minute, it would only be a jump if it was not continuous and this function was continuous. So I'm either going to have a corner or a vertical tangent line. And then at 0, sorry, that's at 0. At 1.5, I should have a horizontal tangent line. Let's check. X to the 3/5 times 4 minus x. I'm graphing the original function. Since I'm only looking between, around 0 and 2, let's change the window. And I really don't care about very many negative numbers. We'll look at a small window in x. And we'll look at a similarly small window in y, minus 5 to 5. What do you see in your picture? A vertical tangent line and a horizontal line. It's worked, master, it's worked. Local extremes happen at critical numbers. Is x equals 0 a local extreme? No. It's not a minimum nor a maximum. It's a place where my derivative fails to exist, right? If the derivative doesn't exist, either I have a jump, a hole, a corner, or a vertical tangent line. Those are the three things. Remember the picture on the first exam where I said, tell me where it's continuous and where it's differentiable? I'm stealing that one. The bottom was equal to 0 there. Remember, my derivative was a fraction. Fractions are undefined when we divide by 0. If the bottom is 0, my fraction is undefined. It's not technically an asymptote, Because I do have a value when I put in 0, right? If I put in 0, I get 0. So technically it's not an asymptote, it's the tangent line that's vertical there. Because the slope is undefined and the lines that have undefined slope are vertical lines. Nicolina.
So. Because it's a straight line at 0, that just does not exist. But 1.5 ends up working because it's actually a extreme dotted line.
I'm confused on the object of the sentence you just gave. At 0, it doesn't exist. What it?
Maybe like extreme.
The thing that doesn't exist at 0 is the slope. Our tangent line has is vertical. Vertical lines have undefined slope. At 0, it's not an extreme. Because the point at 0 is not an extreme. Because there are points to the left of it that are lower than it, and points to the right of it that are higher than it. I thought I saw another hand. Was I hallucinating? I shouldn't be hallucinating. I didn't have anything weird at lunch. Ask me more questions, people. On we go. Local extremes occur at critical values, but not every critical value is an extreme. We just saw that with 0. Okay, an extreme value is either a highest or lowest point. A critical value is a place where my derivative is 0 or fails to exist. I'm sorry, say again. Okay. Yes. I can have as many critical values as I want. There can be only one maximum value and one minimum value. Here is a really nice, simple equation. I promise it's simple. It's a simple equation. What's the derivative sine of x? Where is cosine equal to 0? No. Cosine is not 0 there. What's cosine of 0? 1. Yes, because I was listening. How many critical points do I have? Infinitely many. However, they all have the same maximum value and the same minimum value because they're different points. There's one maximum value for this graph, 1. That's a y value. It just happens a lot. More questions? Local. Top word on the screen there says local. What about absolute? I'll be sloppy with the English. What about absolute extremes? All right, wait a second. The only way I can guarantee myself an absolute extreme is to give you an interval. I don't know the name of that theorem. Yes, ma'am.
Most have.
Must have an interval. I'm writing quickly. My handwriting already sucks, people. Now imagine if I wasn't writing with a fountain pen, it would be even worse. Somebody actually asked me why I don't do the stuff on my iPad and then just email you all my notes. You do not want to see my handwriting with a stylus. So if I give you an interval, then I don't have to actually do as much work. It actually gets easier. Because now I can say, I'm only looking between here and here. It's either going to be the maximum is at a critical point, critical number, or it's at one of the edges. There are only two possible places for me to get a maximum or a minimum. At a critical value or on the endpoints of the picture. But I know the endpoints of the picture are 0 and 3. So I need y values at 0 and 3. Then I need you to find any critical numbers between 0 and 3 and give me a y value for those. Let's do it in the other order. Find me the critical values. This is a polynomial. Its derivative is polynomial. Polynomials are defined everywhere. I don't have to worry about where it's undefined. I only have to worry about where it's equal to 0. And I get x squared equals 1, which gives me two critical values. But why am I being heartless and cruel to x equals -1? Bing. I only care about the numbers between 0 and 3. -1's out of here. Now all you have to do is take those x values and plug them in to f, not f prime, the original equation. So if I put in 0, I get 1. If I put in 1, 1 cubed minus 3 plus 1, I get -1. If I put in 3, I get 27 minus 9 plus 1, I get 19. My maximum value is 19. It occurs at x equals 3. My minimum value is -1. It occurs at x equals 1. Poof. Yes, he's fine. No, I can use this method for any function. As long as I have a closed interval. But again, in that case, I'm going to have to make sure I look for all the critical points of both kinds. Critical points where my derivative is 0 and critical points where my derivative is undefined. I need to make sure I find all the possible critical points within the interval.
How do you-
For, well, that just means f prime is undefined, right? But I'm plugging into f. Since I'm plugging into f, that value can't be undefined. Remember, we said our functions have to have points in the domain. If I think about the function 1 over x, what's the derivative of 1 over x? That's undefined at 0. Zero is not a critical point because 0 is not part of the domain of the function. You have to be in the domain in the first place to be a critical value. So I like finding critical numbers, but I need to remember a critical number must be part of the domain of the function. So f has to exist there. It can be a place where f prime doesn't exist, but f has to exist there. And that means that when I go to plug into the chart, there will be an f at x value. There is an example in the text using trig functions. X minus 2 sine x from minus pi to so positive 0 to 2 pi. That works perfectly well. It's perfectly well defined throughout that entire interval. Even if the derivative is messed up there, I can use the function itself. If you came in late, you have homework for me. Go to the review session tonight. I will see you tomorrow for the exam.